This is pretty cool. This is my first time really working with DACs, digital to analog converters. It's a very simple one using an op amp, a standalone op amp. In this case, it's the LMV358, not to be confused with the LM358. The V means it's rail-to-rail output, which means it can come close to its supply voltage rail in its output, which the stock LM358 can only go to like 3-something volts if you give it a 5-volt input. So that was the first thing I had to overcome, was sort of getting the correct chip, because I just thought, oh, any op amp can be a DAC, whatever. But no, there's more to it than that. And I've got my little rotary display design thing here, which will let me adjust the voltage level now, since it's a DAC. Normally this is a PWM control output on, I think it's digital, it's analog pin, whatever, one of the analog pins over here. Doesn't matter, you can choose any one. It's an analog output. And, oh, I take that back. I'm using it as a digital output. Yeah, that's right. It can be a digital or an analog pin because I'm using the PWM output on this. Anyway, point being, this fan, which is a 5015 fan, is a 2-wire fan. And if you can see this, it starts to blow air, cold, precious air. And now it's off. See that? Based on the PWM control. And this is cool because this fan does not have PWM control. It is only a voltage controlled fan, at least not natively that you can access. It's just got, it's a 2-wire interface, just positive and minus voltage. So I'm actually getting some speed control. If you can hear that getting a little bit louder, just based off of, you know, PWMing a microcontroller. It's pretty cool, folks. There are some limitations, though, which I'll show you, and also some cool little tricks that I found. First and foremost, the RC network that I'm using right now is a 10 kilo ohm and a 10 microfarad. That seems to work pretty well. The capacitor being a lot more important than the resistance. Have a little more leeway on that. The output is going to an NPN transistor, which can drive the higher load required, about 250 milliamps, something like that, to drive the 5015 fan. Now that NPN transistor does have a voltage drop of around 0.8 volts. So even with the rail-to-rail output, I do get 0.8 volts drop. And then even with the rail-to-rail output, I do get something like a 90 millivolt drop across the circuit. So altogether, about a 1 volt drop. Not too bad, especially because if I wanted to use a buck converter to give this 6 volts, I'd probably get exactly what I want. I'd probably get a 5-volt output. In my application for this, not super necessary. The other thing I found, which is interesting, is I was getting some transient stuff here on the oscilloscope. I'm going to go over and switch the oscilloscope. Forgive me, because the camera's going to get wonky for a sec. Burp, 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 boom. I'll go over here to my wonderful little mixed analog digital, mixed analog and digital, yeah, because it uses a CRT still. Oh yeah. Oscilloscope. This thing's pretty cool. We're going to show you what's going on here. So this waveform is the current voltage output. At the bottom here is ground, and there are 1 volt divisions. So right now we're around 2.7 volts. And this is one of the drawbacks, is I'm finding the fan actually does not turn on until I'm around 2.9. So you'll see here, once I get just a little bit higher, right around this range, it starts to kick on. The reason this will actually show a little over 3 volts, because this is actually taking a reading before the voltage droop across the NPN transistor. This is a reading straight from the output of the op amp. And so what's cool is I can turn this knob, this clicky encoder, which is adjusting the PWM frequency, the pulses, the duty cycle, not the frequency, sorry, the duty cycle of the PWM output on the Arduino Nano, the Atmega 328. And it's through the use of the op amp, it's really cool. It's turning this into a constant current DC voltage through the magic of RC networks and op amps. It's very, very cool. A couple things. if I go down below a certain voltage, things get kind of wonky right down here. And that has to do with the capacitor that I added, a 470 microfarad capacitor. I've got to add it close to the fan plug, where it doesn't really do its thing. If I remove that capacitor, that goes away, which is pretty interesting. However, if I start to turn the fan on, you'll see I get all this kind of nonsense that I don't like. And so the capacitor, if I now add it, make sure I get the polarity correct here, fixes all that. So yeah, there's some transients based on current draw, most likely of the fan. I'm not entirely sure why it causes those transients when it's off. Might be a feedback issue with the op amp. It's not, in my use case, it doesn't matter because when the fan's off, it's off. But yeah, this is just a cool way. Camera's gonna be weird for a second here. All right, so this is just a cool way to get yourself some DC controlled stuff happening with an Arduino if you don't have a PWM source or you have something that doesn't like PWM signals, like a DC controlled fan. If I were to give this a PWM signal, it makes a terrible noise and is quite unhappy. And now it's DC controlled. The disadvantage to this particular design with this particular fan, your mileage will vary depending on the fan you use, is it's quite a limited range of change because this fan was simply not designed for what I'm doing. Now I can make it go quite a bit faster, which is nice, but I'd say I only get a reduction, maybe a difference of half the power, like 50%. I can't get it to like a really, really low setting because it'll just cut out, as you see there. And that just has to do with how the fan was designed. So part of me is looking into possibly experimenting with a different fan for this particular design, because I would like to have like total control. But either way, I'm going to count this as a success. My custom board is working. This whole setup is working. A lot of these wires have nothing to do with this particular code that's on here right now. This is a borrow over from previous project. I'm not using the RTC or anything like that. But this is my board that I designed with the op amp. I can kind of zoom in here to show you. And it's pretty straightforward. So you have your positive and negative input here. You have your signal, your PWM input. That goes through this RC network, which is 10 kilo ohm, 10 microfarads. That goes to this op amp. Pin 1, which you see the red wire here going to my oscilloscope probe, outputs to this NPN. And that goes to the output of our fan. I forget if it's an NPN or a PNP now. Oh, on the schematic right in front of me at this moment. There's a couple of the resistors over here that are just meant to properly terminate the second unused op amp, which of course I could configure as a buffer if I really wanted to, but I did not. And then up here we have a fuse, and then this is just some bypass regulation. And this is a trim pot footprint for adjusting the RC network on the fly, if I want to, but I don't need to because I'm doing this. The testing's coming out quite well. That's it for this one.